Scientists have just cracked one of the most important measurements in interstellar astronomy after months of tracking the mysterious visitor known as 3I Atlas with the Hubble Space Telescope. Researchers can now confirm its precise dimensions, 1.3 kilometers in radius, giving it a total diameter of 2.6 kilometers. That makes this cosmic wanderer from another star system roughly the size of a small mountain, and significantly more massive than either of the two previous interstellar objects we've ever detected. But the real revelation isn't about this single object. It's about what this measurement reveals when combined with detection statistics and orbital data. Using the confirmed size of 3I Atlas alongside information from the two earlier interstellar visitors, Oumuamua and Borisov, astronomers have calculated the probability of these objects passing through our solar system. The result is staggering. Statistical models now suggest that approximately one interstellar object crosses through the inner solar system within Jupiter's orbit every single year, every year. Yet we've only managed to confirm 3 detections across nearly a decade of observations. The mathematics tells us something profound. Our solar system isn't isolated. It's constantly being visited by travelers from distant star systems, and we're only just beginning to see them. In this video, we will explain how astronomers achieved this breakthrough measurement of 3I Atlas, why determining its size matters far beyond cataloging one object, what the detection statistics reveal about the hidden population of interstellar visitors streaming through our cosmic neighborhood, and how this discovery transforms our understanding of the solar system's place in the dynamic galaxy around us. Let's get started. The concept of interstellar objects is surprisingly new to astronomy. Throughout most of human history, scientists operated under a straightforward assumption: our solar system was essentially a closed environment. Everything orbiting the sun, every planet, moon, asteroid, and comet, originated from the same rotating disk of gas and dust that collapsed to form our star 4.6 billion years ago. Comets might swing in from the distant Oort cloud on elongated elliptical orbits, but they always came back. Nothing arrived from outside. Nothing permanently left. This framework collapsed on October 19, 2017. Robert Warwick, an astronomer using the Pan-STARRS telescope in Hawaii, detected an object with characteristics that defied explanation within the traditional model. The object was moving at extraordinary velocity, far faster than anything gravitationally bound to the sun should travel. More tellingly, its trajectory wasn't elliptical, it was hyperbolic. The mathematics were clear. This object wasn't captured by our sun's gravity. It was passing through, arriving from interstellar space, and destined to leave permanently. The astronomical community designated it 1I Oumuamua, using a Hawaiian word meaning scout or messenger from afar, arriving first. It was humanity's first confirmed detection of an interstellar visitor, and it raised more questions than it answered. Oumuamua was elongated, roughly 400 meters in length, tumbling through space in a complex rotation. Strangely, it showed no cometary activity, no tail, no outgassing visible in any wavelength. Its slight acceleration away from the sun sparked intense debate. Was it being pushed by radiation pressure? Was there invisible outgassing we couldn't detect? Proposals ranged from exotic ice compositions to more speculative ideas about artificial origins. But the most frustrating aspect of Oumuamua was timing. By the time astronomers realized what they were observing, it was already racing away from the inner solar system. Telescopes scrambled to collect data, but within weeks, the object had faded beyond detection. We managed only a handful of observations before it vanished into the darkness between stars, leaving behind fragmentary data and a transformed understanding of what could visit our solar system. 2 years later, in August 2019, amateur astronomer Gennady Borisov made a discovery that would prove equally significant. Operating from his personal observatory in Crimea, Borisov spotted another object on a hyperbolic trajectory, another confirmed interstellar visitor. This object, designated 2I/Borisov, differed dramatically from Oumuamua in observable behavior. It looked like a comet. It had a visible tail. It was actively outgassing, releasing material as solar heating warmed its icy surface. Spectroscopic analysis revealed familiar chemistry: water ice, carbon monoxide, dust particles. It resembled comets native to our solar system, suggesting that at least some interstellar objects formed through similar processes to the icy bodies we see in our own Kuiper belt and Oort cloud. Crucially, 2I/Borisov was detected much earlier in its approach, providing astronomers with months of observation time rather than weeks. Multiple telescopes tracked it extensively, gathering spectroscopic data, measuring its composition, analyzing its outgassing patterns. By the time it swung around the sun and departed, scientists had accumulated a comprehensive dataset, far more information than we ever obtained from Oumuamua. These two detections established that interstellar objects weren't theoretical curiosities. They were real, observable phenomena that apparently arrived with some regularity, but fundamental questions remained unanswered. How common were these visitors actually? Were we detecting only the largest, brightest examples, while countless smaller objects passed unnoticed? What size distribution characterized the interstellar object population? And critically, what did their existence reveal about planetary system formation and the exchange of matter between stars? 3I Atlas emerged into this context. Discovered in 2025, it represented the third confirmed interstellar visitor and arrived at a time when our detection infrastructure had substantially improved. More sky surveys were operational, pattern recognition algorithms had evolved, the astronomical community knew what signatures to look for. When 3I Atlas appeared, we were prepared to maximize our observations. Measuring the size of 3I Atlas required careful, sustained observation across multiple months. Between November 2025 and January 2026, the Hubble Space Telescope executed a dedicated observation campaign, tracking this fast-moving visitor as it traveled through the inner regions of our solar system. This wasn't straightforward imaging. 3I Atlas was moving at tremendous velocity, faster than any object ever previously observed, passing through our neighborhood. Keeping it centered in Hubble's narrow field of view demanded precise coordination and constant trajectory updates. The observing team collected numerous images across different dates, building what astronomers call a light curve, essentially a record of how the object's brightness changed over time as it rotated and moved relative to the Sun and Earth. But complications arose. During the observation window, Hubble experienced a malfunction in one of its solar panels, creating a frustrating gap in data collection between January 15th and January 18th. Engineers worked to restore normal operations, and once the telescope was functioning properly again, observations resumed. Scientists then processed all the captured images, stacking them together to create a composite view. This technique revealed 3I Atlas moving against the distant background stars. In the processed imagery, the background appears to shift because the software keeps 3I Atlas stationary in the frame, compensating for its motion through space. The observations revealed interesting characteristics. The object showed clear signs of activity, ejecting material into surrounding space, but not in the pattern initially expected. Early data processing suggested a sunward-facing tail, the typical configuration seen in comets, where radiation pressure from the sun pushes released material away from the star. More sophisticated analysis revealed something different. The material streaming from 3I Atlas was actually oriented in the anti-velocity direction. If you imagine 3I Atlas moving forward, the particles were being pushed backward, opposite to its direction of travel. This indicates complex physics at work: dust grains shedding from the surface, plasma interactions with the solar wind, electromagnetic forces acting on charged particles. Space environments operate according to physics that don't match simple Earth-based intuitions. The critical outcome from this observation campaign was the size determination. Calculating the physical dimensions of a distant object requires two essential pieces of information: apparent brightness and surface reflectivity. Brightness alone provides insufficient data. A small, highly reflective object appears just as bright as a large, dark object at the same distance. You need to know the albedo, the fraction of incident sunlight the surface reflects. For 3I Atlas, researchers assumed an albedo of 0.04, meaning the object reflects only 4% of incoming sunlight. This assumption aligns with observations of long-period comets from our own solar system's Oort cloud, which typically display dark surfaces covered in carbon-rich organic compounds. Using this albedo value combined with measured brightness, the team calculated a radius of 1.3 kilometers with an uncertainty of plus or minus 0.2 kilometers. This translates to a diameter of approximately 2.6 kilometers, just under 2 miles across. This measurement places 3I Atlas significantly larger than both previous interstellar objects. Oumuamua measured roughly 400 meters at its longest dimension. 2I/Borisov had an estimated diameter around 500 to 600 meters. 3I Atlas is 4 to 5 times larger than either predecessor. Some early speculative estimates had suggested it might reach 50 kilometers across, which would have been extraordinary, potentially the largest cometary body ever observed. The confirmed 2.6-kilometer diameter places it comfortably within normal parameters for cometary objects, though toward the larger end of that distribution. To provide context, 2.6 kilometers is comparable to the height of Mount Vesuvius, the volcano that famously destroyed Pompeii. It's roughly half the length of Manhattan Island. An object of this size, impacting Earth, would constitute an extinction-level event, releasing energy equivalent to millions of nuclear weapons simultaneously. This is not a minor piece of debris, it's a planetesimal, a substantial fragment left over from planetary formation in whatever distant star system originally hosted it, now wandering interstellar space on a trajectory that randomly intersected our solar system. As of early February 2026, 3I Atlas occupies the space between Mars and Jupiter's orbits, currently positioned at approximately 5.2 astronomical units from the Sun. 1 astronomical unit, abbreviated AU, represents the distance from Earth to the Sun, roughly 150 million kilometers. Mars orbits at about 1.5 AU. Jupiter sits at 5.2 AU. 3I Atlas entered our solar system from beyond Neptune's orbit back in 2016, passed its closest approach to the Sun, termed perihelion, in late 2025, and is now traveling outward. It will make its closest approach to Jupiter on March 17, 2026, after which it will continue accelerating away, eventually exiting our solar system permanently. The object's trajectory is what astronomers classify as hyperbolic, unlike the elliptical orbits characterizing planets and native comets, which loop around the Sun in predictable repeating patterns. A hyperbolic trajectory is one way. The object arrived from interstellar space, curved around the Sun due to gravitational influence, but possessed sufficient velocity to escape. Solar gravity will tug on it, deflect its path, slow it marginally, but cannot capture it. 3I Atlas will depart our solar system and continue traversing the galaxy until potentially encountering another stellar system, possibly millions of years hence. The significance of measuring 3I Atlas extends far beyond characterizing a single object. This measurement provides a critical data point for understanding an entire population that has remained largely invisible until now. The central question becomes, how many interstellar objects actually exist in our cosmic vicinity? Researchers approach this problem through statistical modeling. They possess 3 confirmed interstellar detections: Oumuamua in 2017, 2I/Borisov in 2019, and 3I Atlas in 2025. They had size estimates for all 3 objects. They had trajectory data showing where these visitors traveled through our solar system. And they possessed detailed information about our detection capabilities, which telescopes operated during what periods, which regions of sky received monitoring, on what detection thresholds applied for objects of varying sizes and brightness levels. Using this foundation, researchers constructed a statistical model. If we detected 3 interstellar objects spanning approximately 8 years, and if those objects possessed the measured sizes we determined, how many total interstellar objects must pass through our solar system to produce that observed detection rate? The calculation must account for observational bias. Larger objects are inherently easier to detect than smaller ones. Brighter objects are more readily spotted than dark ones. Objects passing close to Earth are more detectable than those remaining in the outer solar system. Objects arriving when multiple sky surveys are operational have higher detection probability than objects that passed through decades earlier, when we had fewer telescopes and less sophisticated algorithms. The results proved remarkable. According to recent research analyzing this question, approximately 1 interstellar object should pass within 4.5 astronomical units of the Sun every year. That distance, 4.5 AU, sits just inside Jupiter's orbit, representing the inner and middle regions of our solar system, where detection probabilities are highest because objects there are relatively close, reasonably well illuminated by sunlight, and located in sky regions that surveys monitor with some regularity. 1 per year, we've confirmed 3 detections across 8 years. That mathematics indicates we're missing roughly 80% of the interstellar objects passing through this region. They exist, they're real, they're moving through the space between Mars and Jupiter, and we're failing to detect them. Why are we missing so many? Multiple factors contribute. First, many objects are likely small and dark. If an object measures only a few hundred meters across and possesses low albedo, it will appear extremely faint even when relatively close to the Sun. Our telescopes can theoretically detect such objects, but only if we're observing precisely the right patch of sky at precisely the right moment. Second, interstellar objects move extraordinarily fast. They're not gravitationally bound to the Sun, so they travel at velocities of 20, 30, sometimes exceeding 40 kilometers per second. They transit the inner solar system in months, sometimes mere weeks. If a survey happens to be pointed elsewhere when the object is at peak brightness, we miss it entirely. Third, these objects don't always behave predictably. Some exhibit comet-like activity, developing tails and comas that increase visibility. Others, like Oumuamua, remain inert, essentially dark chunks of material reflecting minimal light. Now expand the analysis beyond 4.5 AU. When considering the region extending to Neptune's orbit at 30 AU, the volume of space increases dramatically. We're no longer discussing a relatively narrow disk around the Sun. We're addressing a vast spherical volume extending above and below the solar system's primary plane. Interstellar objects aren't constrained to follow the ecliptic, the flat plane where planets orbit. They can arrive from any direction, above, below, from any angle, and our detection capabilities in those regions are severely limited. Within that larger volume, the number of interstellar objects present at any given moment could number in the dozens, potentially hundreds. They're drifting through the Kuiper belt, moving through the space between Uranus and Neptune, passing above or below the orbital plane where few surveys ever look. Most will never be detected. They'll transit our cosmic neighborhood completely unnoticed, invisible travelers on journeys that began light years distant. This realization fundamentally restructures our understanding of the solar system. We previously conceptualized it as an isolated island, a closed system shaped entirely by the Sun's gravitational influence and the primordial material that condensed here 4.6 billion years ago. We now understand that model is incomplete. Our solar system is porous. It experiences constant visitation by material originating in distant stellar systems. We inhabit a dynamic galactic environment where matter flows between stars, where planetary systems exchange material across millions and billions of years, where the fundamental building blocks of worlds wander the galaxy until gravity draws them into new orbits around new suns. The implications extend deeper still. If interstellar objects are this common in the present era, they must have maintained similar frequency throughout Earth's entire history. These visitors have been arriving for billions of years, long before human civilization, long before complex life, long before any life existed. Some inevitably impacted Earth or other planets. Some may have delivered organic compounds, water, or other materials that contributed to the chemical evolution, eventually producing life. We've long understood that asteroids and comets from within our solar system bombarded the early Earth, possibly delivering the water filling our oceans and the organic chemistry enabling biology. Now we must consider that some impacts may have arrived from interstellar space, carrying chemistry from entirely different stellar systems, potentially seeding Earth with biological building blocks that originated light years away. The confirmation that interstellar objects regularly visit our solar system carries practical implications extending well beyond academic curiosity. One immediate concern involves planetary defense. NASA and other space agencies operate programs dedicated to detecting and tracking near-Earth objects, asteroids and comets that could potentially impact our planet. The objective is cataloging as many objects as possible, calculating their orbits, and identifying any posing collision risk years or decades ahead of potential impact. Interstellar objects introduce complications into this mission. They don't follow predictable orbits. They arrive from random directions traveling at high velocities with essentially no advance warning. Oumuamua was detected as it was already departing the inner solar system. If an object similar to 3I Atlas were on an Earth collision trajectory rather than passing harmlessly through the asteroid belt, we would have extremely limited response time. The object might be detected months before impact, possibly only weeks, far too brief for mounting any deflection mission using current technology. This doesn't mean interstellar object impacts are probable. Space is vast, Earth is small. The probability of any specific interstellar object striking our planet remains extremely low, but extremely low differs fundamentally from zero, and when the potential consequence involves civilization-ending impact, even low-probability scenarios demand serious attention. Understanding that approximately one interstellar object per year passes within Jupiter's orbit means we require detection systems capable of spotting these visitors as early as possible, ideally while they're still beyond Neptune's orbit, providing maximum warning time. Next-generation sky surveys become critical here. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the Legacy Survey of Space and Time, or LSST, commencing operations in the mid-2020s. This observatory will photograph the entire visible sky every few nights, creating a continuously updating map of everything that moves or changes. It will detect asteroids, comets, supernovae, variable stars, and crucially, interstellar objects. With LSST operational, our capability to find these cosmic visitors will increase by orders of magnitude. We'll begin detecting interstellar objects while they're still in the outer solar system, providing months or years for study instead of weeks. We'll measure their sizes, compositions, rotation rates, and activity levels with unprecedented precision. We'll construct a statistical census revealing what object types exist, what materials comprise them, how their properties vary, and critically, we'll identify any posing threats far enough in advance to enable response. Beyond planetary defense, the scientific value of detecting additional interstellar objects is extraordinary. Each represents a sample from another stellar system delivered directly to our doorstep. We don't need to dispatch spacecraft across light years of distance to study exoplanetary systems. The galaxy delivers samples naturally. By analyzing interstellar object composition, we learn what materials exist around other stars, whether they resemble what we have in our solar system or differ fundamentally. For example, 2I/Borisov exhibited evidence of carbon monoxide in its outgassing at concentrations higher than typical solar system comets. That reveals something about the chemistry of its origin system, possibly indicating different formation temperatures or different abundances of volatile elements. 3I Atlas, with its larger size and activity evidence, provides another data point. As we detect more objects, patterns will emerge. Are most interstellar objects icy and comet-like, or do rocky asteroids occur commonly? Do they cluster in certain size ranges, or does a continuous distribution exist from small fragments to massive planetesimals? What does population distribution reveal about planetary formation processes in other stellar systems? There exists the tantalizing possibility of sending spacecraft to intercept an interstellar object. This was seriously proposed for both Oumuamua and 2I/Borisov, though neither mission advanced due to extreme velocity requirements and short timescales. With improved advanced detection, rapid response missions become more feasible. Imagine a spacecraft designed for short-notice launch, capable of intercepting an interstellar visitor while it's still in the outer solar system, matching its velocity and accompanying it for months, conducting detailed observations and potentially returning samples to Earth. This would represent the ultimate form of interstellar exploration, studying another star system's material without leaving our cosmic neighborhood. The technology for such missions exists within current capabilities. We possess the rockets, propulsion systems, and instruments. What we require is early detection and sufficient warning time. With LSST and future surveys, that becomes achievable. We could launch our first interstellar object rendezvous mission within the next decade, depending on when the next suitable target appears. Looking further ahead, studying interstellar objects connects to one of science's most profound questions: how common are planetary systems resembling ours, and what does the architecture of other systems reveal about our own formation? Every stellar system forms from a disk of gas and dust. Planets coalesce from that material, accumulating most available mass, but not all. Leftover planetesimals, the building blocks never incorporated into planets, remain scattered throughout the system. Some experience gravitational ejection through interactions with giant planets flung into interstellar space at high velocities. Our solar system executed this process. Jupiter and Saturn, During their early migration and gravitational interactions, scattered countless objects. Some fell into the sun, some were ejected entirely, sent on one-way journeys into the galaxy. That means our solar system has contributed to the interstellar object population. Somewhere in the galaxy, fragments of our Kuiper belt are wandering between stars, just as fragments from other systems visit us. By studying interstellar objects arriving here, we're essentially sampling the debris fields of distant planetary systems. We're observing what remains after planets form. We're learning about the ejection processes shaping planetary system architecture, and we're gathering clues about how common different planetary system types are across the galaxy. For instance, interstellar object size distribution reveals information about planet formation efficiency in other systems. If we detect mostly large objects like 3I Atlas and very few small ones, that suggests certain formation processes dominate. If we find wide size variation, that indicates a different story. Composition ratios, how many icy objects versus rocky objects, can indicate original protoplanetary disk composition, which depends on parent star metallicity and conditions in the molecular clouds where those stars formed. This constitutes galaxy-scale archaeology. We're using debris from ancient planetary formation events to reconstruct the history of stellar systems across our local Milky Way region. And it begins with measurements like the one just completed for 3I Atlas. One size estimate, combined with detection statistics, opens a window into understanding billions of years of galactic evolution. There's also a human dimension to this story that deserves recognition. For thousands of years, humans have gazed at the sky, wondering what else exists beyond our world. Are we alone? Are there other worlds? What exists beyond familiar planets and stars? Throughout most of history, we could only speculate. Now we're living in the era when we're discovering answers. Not through radio signals from alien civilizations, but through direct physical evidence. Rocks from other stellar systems, ice from alien environments, material that formed around stars we cannot even identify. Now drifting through our cosmic neighborhood, carrying information encoded in chemistry and structure, we didn't need to construct starships to find this material. It came to us. The galaxy delivered samples to our doorstep, and we finally possessed the technology to notice them. That's remarkable. It demonstrates that the barrier between us and the rest of the galaxy is lower than we imagined. We're not isolated. We're connected. Matter flows between stellar systems. Chemistry exchanges across light years. The galaxy is a more dynamic, interactive environment than the static model we once accepted. And we're only beginning this discovery process. 3 confirmed interstellar objects, statistical models, suggesting dozens more pass unnoticed every decade. Observatories coming online that will increase detection rates by factors of 10 or more. Within a generation, we'll likely have detected hundreds of interstellar visitors. We'll possess data on their sizes, compositions, velocities, and origins. We'll begin viewing them not as rare anomalies, but as routine components of the solar system environment. Cosmic commuters passing through on billion-year journeys across the galaxy. Right now, in February 2026, 3I Atlas is traversing the space between Mars and Jupiter, approaching its closest encounter with the solar system's largest planet. Within weeks, it will swing past Jupiter at a distance that, while safe, represents the nearest approach a confirmed interstellar object has made to one of our gas giants. Astronomers will continue tracking it, gathering data on how Jupiter's immense gravity affects its trajectory, measuring any outgassing or activity changes as it moves through different solar system regions. Within months, 3I Atlas will cross Jupiter's orbit and continue outward, passing through the asteroid belt region, moving toward the outer planet's realm. Within a year, it will travel beyond Saturn. Within a decade, it will pass Neptune's orbit, entering the Kuiper belt region where it first entered our detection range in 2016. And then, within additional decades, it will depart entirely, fading into interstellar space's darkness, traveling onward to whatever destination the galaxy's gravitational currents direct it. But 3I Atlas doesn't represent the end of this story. It's a chapter in a much longer narrative, spanning billions of years and light years of space. Somewhere in the cosmos, right now, other interstellar objects are approaching our solar system. They're invisible to us currently, too distant, too dark, moving through space regions we don't monitor. But they're approaching. And with each passing year, our ability to detect them improves. Our sky surveys advance, our algorithms become more sophisticated, our understanding deepens. Within the next few years, we'll detect interstellar object number 4, then 5, then 10. Each will add to our knowledge base. Each will be a messenger from a different stellar system, carrying information about worlds we cannot visit, chemistry we've never sampled, history we're only beginning to comprehend. And with each detection, the realization becomes more concrete. We are not isolated. Our solar system participates in a galaxy-wide network of matter exchange, a cosmic ecosystem where material flows between stars, where the building blocks of worlds wander for millions of years before finding new homes. This is the genuine significance of measuring 3I Atlas. It's not about characterizing one object, it's about revealing a hidden population that has surrounded us throughout our existence. It's about understanding that the galaxy is more interconnected than we previously conceived. It's about recognizing that Earth, our solar system, our sun, exist within a dynamic environment shaped by forces and processes spanning the entire Milky Way dot. And it's unfolding now. The discoveries are being made today. The data is being collected this year. The papers are being published this decade. We are living through the era when humanity transitions from believing we inhabit a static, isolated solar system to knowing we're part of a galactic community of matter and energy, constantly exchanging material, constantly interacting, constantly evolving. The size of 3I Atlas is 2.6 kilometers. But the implications of that measurement stretch across light years and billions of years, connecting us to stellar systems we've never observed, to planetary formation events that occurred before our sun existed, to a future where interstellar objects are as familiar to us as comets and asteroids, regular visitors from the wider galaxy that we study, track, and eventually, perhaps, explore directly. The universe is more connected than we imagined. The galaxy is more active than we thought, and we're finally developing the eyes to see it. If you're fascinated by these discoveries and want to stay updated on the latest astronomical breakthroughs, please subscribe to our channel. We're working to reach 1,000 subscribers who share our passion for making cutting-edge space science accessible to everyone. Hit that subscribe button and join our growing community of space enthusiasts. Every subscription helps us continue bringing you in-depth coverage of discoveries like 3I Atlas. Thank you for watching, and we'll see you in the next video.